Chapter 12, Counter Circuits and Applications. In this chapter we will discuss simple counters used for counting program counters or counting various values incrementing up. Analysis of sequential circuits is a mixture of combinational logic gates and flip-flops. We can see this through the examples. Example 12.1. The 7474 shown in figure 12.3 is a positive edge triggered D flip-flop. The waveforms shown in figure 12.4 are applied to the inputs at A and CP, the clock pulse. We'll then sketch the resultant waveform at D, Q, Q0, and X. We have some following stipulations for this, where Q equals 0, Q0 equals 1 during 0 period because of the RD, the reset. D is equal to A Q0 and X is equal to AQ. Therefore, the level of D and X will change whenever the inputs to the AND gates change regardless of the state of input clock. At the positive edge of the pulse, D is high, so Q will go high and Q0 will go low and remain there until the positive edge of the pulse 2. During period 1, D will equal AQ0 and X will equal AQ as shown. At the positive edge of pulse 2, D is low, so the flip-flop will reset. At the positive edge of pulse 3, D is high, so the flip-flop will set. This is shown here. You have clock pulse times 0, reset just sets, and the input is A, and you have your Q as your output, and your X equals A times Q to get your resultant waveform. Using the same circuit in example 12.1, we now sketch the waveforms at D, Q, Q0, and X, given the input waves shown in figure 12-5. This is the same sort of thing, except we have a different A. And our times, we just translate them down and draw our resultant waveform dependent on our set value, making sure that it's set. Then we start our clock pulse and work our way through to get to X. Now we'll show you the 74LS112. This is shown in figure 12-6. It's a negative edge triggered flip-flop. This is unique because it has a toggle mode. So we'll go through the waveform and determine the toggle modes between the chip. You have first, you have your set, so that starts, you have your clock pulse, and you have your input. Now we have our J and our K, and those correspond to their specific functions. You have your Q and your Q1. Your Q1 has various hold states, has to wait till a full clock pulse to start, and it toggles. And it holds again on the next 2 clock pulses, and then it resets 2 after that. Ripple counters are JK flip-flops, and flip-flops used to form binary counters. Cascade one output to the next input. This is what a ripple counter is. For a 3-bit counter, you use 3 flip-flops. That is 2 to the 3rd equaling 8 different combinations, which is 0, 0, 0, 3, 1, 1, 1. Its modulus is 8, so you can call it a mod 8 counter. We use the toggle mode in these types of counters. With this example, we have 3 counters set together on the output of one connects to the clock pulse of the other, and we have our resets set together as well. This allows us to count all the way up from 0 all the way to 7, and then it resets and then goes through the same cycle again through our flip-flops. Propagation delay skews the waveform sometimes, and this can be shown via figure 12-11. You have a small propagation delay that occurs between each of the different flip-flops. For instance, the first flip-flop to the 0 has a propagation delay, a small propagation delay of about 20 nanoseconds between the second flip-flop 2 to the 1, and the same thing with 2 to the 1 to 2 to the 2 when it switches over, because it has to take time to get through the flip-flop and set itself up for the output. This is another example of a 4-bit ripple counter. This one counts from 0 all the way to 15 and then resets back to 0 and recounts. It's a sequential counter going all the way up without skipping a number. You can also make a ripple counter count down. It takes the binary outputs from the not Q outputs instead of the regular Q. So this counts from 7 down to 0 because the Q is connected to the clock pulse and the Q naught is connected to your output instead. Design of divide by n counters. This reduces the frequency of periodic waveforms. There's an example of a divide by 5 mod 5 counter. This is the mod 5 counter. You have 3 JK flip-flops connected together along with your reset with a NAND gate. This allows you to count from 0 to 4 and back to 0 to 4 again due to the reset flip-flop to 0. When it's 5, 1, 0, 1 is reached. This is designed with the NAND gate function. The 7493 is a 4-bit binary ripple counter. This is the IC form of the ripple counter. This can be seen here in this diagram with the pinout of the chip correspondent to the internal diagram of that same chip. We use this top display 1231 as a mod 16 and the figure 12-32 is a mod 12. We also use 7490 and 7492 to achieve the same function. Some system design applications. An LED illuminates for 1 second once every 13 seconds. This is done by using the 7490 in sequence with the 7492. This is another mod 10 counter that turns on and off dependent on the flip-flop output. Design application
is a digital clock capable of hours, minutes, and seconds. This is seen in example 1219. We have designed to read from time 000000, which is hours, minutes, and seconds, to 11:59:59. Doing this, you connect a mod 2 to a mod 10 to a mod 6 to another mod 10 to another mod 6 to another mod 10. This counts your hours with the mod 2 and the mod 10, your minutes with the mod 6 and mod 10, and then your seconds again with the mod 6 and mod 10. The mod 6 and mod 10 count from 0 to 59, and your mod 2 plus mod 10 count from 0
to 11. There's a 7-segment LED display decoders, the 7447, that are used. These counters must output BCD. They're a common anode LED display. You can see the physical LED layout and the pinout for the LED display. It's an 8-bit LED display noted by the A, B, C, D, E, F, and G, and you have your decimal point as well. The drivers need to be active low outputs, and there's also a common cathode LED display that's an active high output. And you can drive a multiplex display with the microcontroller to save power, and it's not all displays are on at once. As in this example, you can have one display on, or one piece of one display on at a time. And this is a truth table for that same BCD to 7-segment decoder for the display. So you take your 4 bits and they correspond to a different value with your A, B, C, D, E, F, and G segments of your 7-segment display. A synchronous counter. All clock inputs are tied to a common clock line. The 4-bit synchronous counter is a mod 16, which uses 4 flip-flops as shown here. This counts from 0 to 15, and it resets as well. This is a different form of the mod 16 previously shown. It is a synchronous counter that has all clock pulses tied together instead. You can use the 74192 or the 193 with this. It's either decade counter or binary counter. As shown here, you have a simple chip design for it, and your truth table, function table inputs and outputs dependent on whether you're using your reset, parallel load, or counting up or counting down functions. Some applications of synchronous counters count to 0 to 9 or 9 to 0 and 0 to 9. You can divide by 9 frequency divider using the 74193, or divide by 200 using the synchronous counters.
Important that flip-flops are used to toggle. They can be cascaded end-to-end to form ripple counters. Ripple counters cannot be used in high-speed circuits because of the problem they have with accumulating propagation delay through all the flip-flops. A down counter can be built by taking outputs of the Q naughts of a ripple counter, and any modulus or divide by counter can be formed by resetting the basic ripple counter when a specific count is reached. A glitch is a short duration pulse that may appear on some of the output bits of a counter. You have your ripple counter chips, 7490, 7492. 4-bit counter ICs can be cascaded end-to-end to form counters with higher than mod 16 capability. And you have your 7-segment display, which displays these counter values. If you wish, you connect it to a decoder to do this, and they're constructed with either cathodes or anodes connected to the common pin.